Hello, and welcome to this very brief presentation where we consider the relationship between linear and angular velocity. So we're going to derive the formula v is equal to omega r, where v is the linear velocity, and that varies across the flywheel shown here from zero velocity at the centre to the maximum velocity at the periphery or at the rim of the wheel. So in other words, the greater the radius r from the centre, the greater the linear velocity, but the angular velocity will remain constant. The derivation shown in this presentation is just a standard extract from an engineering textbook. This presentation just outlines the derivation. The derivation does assume you're familiar with radian measure and also with linear motion equations. There are separate presentations on both of these topics. So here's a brief overview of the relationship between linear and angular velocity. If we consider a flywheel of radius r, shown in the sketch here, and it's rotating about point O, shown here, with a uniform or constant angular velocity omega here. After time t, the flywheel has rotated through an angle denoted as theta in the diagram. A point on the rim moves a linear distance s, shown here, with a uniform linear velocity v. That's from A to B, shown here. Now, from radian measure, we know that arc length s is equal to the radius multiplied by the angle turned through theta. But we also know from previous work that the angular displacement, theta, is equal to the angular velocity multiplied by the time taken. So we can write the s equals to r theta in terms of s is equal to r, replacing the theta with omega t. We'll label that equation 1 for reference. Now we also know from our previous work on linear motion that the distance s is calculated from linear velocity multiplied by time. In other words, s is equal to v multiplied by t. Call that equation 2. If we now equate equations 1 and 2, we form this equation: Vt is equal to r omega t. And noting that the t cancels on both sides of the equation, we're left with the equation V is equal to omega r. And as I say, that's now a very useful equation because it relates linear velocity v to angular velocity omega. Here's a brief illustration on application of the formula we derived previously, V is equal to omega r. If the flywheel, shown here on the right hand side, has a constant angular velocity of 3000 rpm, so that would be omega in our diagram, we've got to calculate the linear velocity at the rim, labelled v. The flywheel's diameter is stated as 400 millimeters. So, extracting the information from the question, angular velocity capital Omega is 3000 rpm. Notice I've converted that to angular velocity lowercase omega in radians per second. So that's 3000 multiplied by 2 pi divided by 60. So that's 50 pi radians per second. The diameter, d, from the question is 400 millimeters. Converted that to meters, so 0.4 meters. So therefore the flywheel's radius to the rim is 0.2 meters. Just notice I'm using uppercase r for radius in my calculation, but lowercase r was stated on the diagram. From the formula, v is equal to omega r, so to find linear velocity v, simply insert the values, so that's omega is 50 pi and the radius is 0.2. So the linear velocity at the periphery of the flywheel is 10 pi meters per second, or to 4 significant figures at 31.42 meters per second. So that's a brief illustration of how to use the formula V is equal to omega r.